Picture this, 640 light-years away, a stellar monster lurks in Orion. This red supergiant is so massive that if placed at the center of our solar system, its surface would extend beyond Mars. It burns through nuclear fuel at a ferocious rate, and when it dies, the explosion will be visible from Earth in daylight, outshining every star for months. This is Betelgeuse, and NASA watches it around the clock because something unprecedented is happening. Recent discoveries suggest this stellar giant may not be alone, potentially rewriting everything we know about the most dangerous stars in our galaxy. But here's the twist: while Betelgeuse captures headlines as everyone's favorite supernova candidate, an even more sinister class of stellar objects lurks in the cosmic shadows. Objects so dangerous that a single outburst could strip away Earth's protective ozone layer from thousands of light-years away, leaving our planet defenseless against deadly ultraviolet radiation. Welcome to the terrifying world of stellar threats, where the universe's most extreme objects wage a constant battle between creation and destruction. Today, we're exploring the cutting-edge science behind NASA's intensive stellar monitoring programs and revealing why some stars demand constant vigilance from our most advanced space telescopes. Before examining the specific star that has NASA's undivided attention, we need to understand the cosmic threat landscape. Not all dangerous stars are created equal, and their threat mechanisms vary dramatically in both destructive potential and likelihood. At the foundation lie supernovae, the explosive deaths of massive stars. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, the balance between gravitational collapse and radiation pressure fails catastrophically. The core implodes in milliseconds, creating temperatures and pressures that forge the heaviest elements before rebounding in an explosion that can outshine an entire galaxy. The danger to Earth isn't immediate annihilation, it's insidious. High-energy radiation and cosmic rays from these explosions can travel vast distances, and if a supernova occurs within roughly 25 light-years of Earth, the consequences could be devastating. The radiation would tear apart molecules in our upper atmosphere, particularly nitrogen and oxygen, causing them to recombine into nitrogen oxides that would destroy our protective ozone layer. Without this shield, Earth would be bathed in lethal ultraviolet radiation. Photosynthetic microorganisms, the foundation of our food chain, would be cooked by increased UV exposure. Marine ecosystems would collapse as phytoplankton populations crashed. Crop failures would be widespread, and radiation would cause skyrocketing rates of skin cancer and other illnesses. But supernovae represent just one tier of the stellar threat hierarchy. Above them lurk gamma-ray bursts, cosmic phenomena so powerful they can sterilize planets across thousands of light-years. These events, often associated with the collapse of massive stars or neutron-star collisions, focus energy into narrow beams that punch through galactic distances with devastating efficiency. At the apex of stellar danger sit magnetars, neutron stars with magnetic fields so intense they defy comprehension. These cosmic monsters possess magnetic fields a quadrillion times stronger than Earth's, generating starquakes that release more energy in seconds than our Sun produces in years. When a magnetar experiences one of these seismic events, it unleashes a gamma-ray burst that makes a typical supernova look like a firecracker. The December 27, 2004 magnetoflare demonstrates these objects' power. SGR 1806-20, located 50,000 light-years away, experienced a starquake lasting just 1/10 of a second. Yet the gamma-ray burst was so intense it temporarily disrupted Earth's ionosphere, interfering with radio communications and satellite operations. If that same magnetar had been just 10 light-years away, the radiation would have triggered a mass extinction event. Now, let's examine the star that has become the poster child for stellar threats, Betelgeuse. This red supergiant achieved fame largely due to a dramatic dimming event in late 2019 that sent ripples of excitement and concern through both scientific and public communities. Betelgeuse is a stellar giant in every sense, with a mass 20 times our Sun and a radius varying between 700 and 1,000 solar radii. It's so enormous that if it replaced our Sun, its surface would engulf Mercury, Venus, Earth and Mars. This immense size results from its advanced evolutionary state. Betelgeuse has exhausted its hydrogen core and now burns heavier elements in a desperate attempt to maintain radiation pressure against gravitational collapse. This process of burning progressively heavier elements, from hydrogen to helium, then carbon, oxygen, silicon, and finally iron, accelerates rapidly. While our Sun will burn hydrogen for 10 billion years, Betelgeuse will exhaust its nuclear fuel in just a few million years total. The star is in the final stages of this process, making it a prime supernova candidate. The 2019 dimming event that thrust Betelgeuse into the spotlight was unprecedented. Between October 2019 and February 2020, its brightness dropped by more than 60%, visible to the naked eye. For a star relatively stable for over a century, this dramatic change sparked intense speculation about an imminent explosion. NASA's response was swift and comprehensive. Hubble was immediately tasked with monitoring Betelgeuse across multiple wavelengths, while ground-based observatories joined a coordinated campaign. What they discovered was both fascinating and reassuring. Betelgeuse hadn't exploded, but had experienced a surface mass ejection event, essentially a stellar flare on a scale dwarfing anything our Sun could produce. Hubble revealed that Betelgeuse had ejected superheated material from its surface, roughly 400 billion times more mass than a typical solar coronal mass ejection. This material rapidly cooled as it expanded, forming a dust cloud that temporarily blocked much of the star's light. This event provided astronomers with an unprecedented glimpse into the violent processes of massive stellar evolution. The mass ejection literally blew away a portion of Betelgeuse's photosphere. Subsequent observations showed the star slowly recovering, rebuilding its outer layers while continuing its march towards supernova. Just when astronomers thought they had Betelgeuse figured out, the star threw another curveball. In 2024 to 2025, studies began converging on a startling possibility. Betelgeuse might not be alone. Evidence for a hidden companion star, dubbed Beetle Buddy, has been building steadily, potentially explaining puzzling aspects of Betelgeuse's behavior. The story begins with long secondary periods, LSPs. About one-third of cool luminous stars like Betelgeuse exhibit these mysterious brightness variations over several years. For Betelgeuse, this cycle lasts approximately 2,100 days, roughly 6 years, and has been observed for over a century. Despite extensive study, the causes remain perplexing. Various theories have been proposed. Some suggested internal pulsations driven by complex interactions between stellar layers. Others proposed dust cloud formation or giant convection cells bringing hotter or cooler material to the surface. However, recent analysis revealed patterns difficult to explain with internal mechanisms. The star exhibits not just brightness variations, but periodic changes in radial velocity, its movement toward or away from Earth. These velocity changes follow a 36-year cycle correlating with longer-term brightness variations, suggesting external influence. Enter the Beetle Buddy hypothesis. Computer models suggest a companion star with 0.5-2 solar masses, orbiting Betelgeuse at a distance comparable to Saturn's orbit around the Sun, could explain these phenomena. Its gravitational influence would create tidal forces, driving the observed variations while explaining Betelgeuse's unusually rapid rotation of 15 kilometers per second. The search for this companion has become an intensive stellar detective story. In 2025, Jared Goldberg's team used Hubble's Space Telescope imaging spectrograph to search for the companion in far ultraviolet light, timing observations for maximum separation when detection would be most likely. Despite sophisticated instruments and careful timing, the search found nothing conclusive. However, this doesn't rule out Beetle Buddy's existence. The hypothetical companion is likely a small, cool star easily overwhelmed by Betelgeuse's brightness, especially during recent dimming events when dust clouds made detection challenging. The implications extend beyond solving brightness variations. If confirmed, a companion could significantly influence the timing and nature of Betelgeuse's eventual supernova. Binary interactions can trigger earlier explosions, alter explosion mechanisms, or even prevent certain types of supernovae. Understanding whether Betelgeuse has a companion is crucial for predicting its final fate. The monitoring of Betelgeuse represents just one component of NASA's comprehensive stellar surveillance network, a sophisticated array of space telescopes tracking the most dangerous cosmic objects. This network operates continuously, gathering data across the electromagnetic spectrum to provide early warning of potential threats. At its heart sits the Hubble Space Telescope. Since 1990, Hubble has revolutionized our understanding of stellar evolution and monitored potentially dangerous stars like Betelgeuse. Its ability to observe in ultraviolet, visible, and near-infrared light makes it valuable for studying outer atmospheres and mass loss processes of evolved stars. Hubble's observations of Betelgeuse have been revealing. Its high resolution has allowed astronomers to create the first direct images of the star's surface, showing a mottled pattern of hot and cool regions that illuminate convective processes. More importantly, Hubble's ultraviolet capabilities have been crucial for detecting mass ejection events that make Betelgeuse so unpredictable. Complementing Hubble is the James Webb Space Telescope, NASA's newest and most powerful observatory. Webb's unprecedented infrared sensitivity is ideal for studying dust clouds surrounding evolved stars like Betelgeuse. Its ability to peer through dust has provided new insights into the material ejected during Betelgeuse's 2019 outburst. The network extends beyond these flagship missions. Chandra X-ray Observatory monitors high-energy emissions, providing crucial data about violent processes around dangerous stars. For monitoring magnetars, NASA relies on specialized missions like the Imaging X-ray Polarimetry Explorer, XPE, which measures X-ray polarization to reveal the structure of intense magnetic fields. Recent XPE observations have shown how these objects generate and focus their devastating gamma-ray emissions. The coordination between observatories is remarkable. When a potentially dangerous stellar event is detected, alerts automatically trigger coordinated observation campaigns across multiple wavelengths. This multi-messenger approach has proven invaluable for understanding complex stellar physics. Ground-based observatories also play a crucial role. Automated survey telescopes continuously scan for transient events, detecting stellar explosions within minutes of occurrence. The data is processed by sophisticated algorithms that identify patterns indicating potential threats, allowing astronomers to respond quickly. While Betelgeuse captures public attention, astronomers know the most immediate stellar threats come from magnetars. These ultra-dense remnants of stellar explosions represent the most extreme magnetic environments in the universe, with destructive capacity far beyond conventional supernova. Magnetars are neutron stars, collapsed cores of massive stars that have undergone supernova explosions. When a star 25 times our Sun's mass exhausts its fuel, the explosion blasts away outer layers while crushing the core into an object just 20 kilometers in diameter but containing more mass than our entire Sun. The density defies comprehension. A teaspoon of neutron star material would weigh approximately 6 billion tons, roughly Mount Everest compressed into a volume smaller than a sugar cube. At these densities, normal atomic structure breaks down completely. Magnetars take this extreme physics further. While typical neutron stars possess magnetic fields about 1 trillion times stronger than Earth's, magnetars boast fields a quadrillion times stronger. This field is so intense it would be lethal at 1,000 kilometers, disrupting atomic structure at closer ranges. The true danger lies in sudden outbursts. The intense magnetic fields create enormous stresses in the neutron star's crystalline crust. When these stresses exceed the breaking point, the resulting starquake releases staggering energy. In a fraction of a second, a magnetar can release more energy than our Sun produces in a year, channeled into focused gamma-ray beams. Recent discoveries reveal magnetars are more common and active than previously thought. The closest known magnetar, XTEJ 1800-10197, lies just 8,000 light-years away, close enough that a major outburst could threaten our biosphere. This particular magnetar has exhibited unprecedented behavior since 2018, emitting circularly polarized radio waves never before observed from astronomical objects. The 2024 to 2025 observations of XTEJ 1800-10197 reveal emission patterns challenging our understanding of magnetophysics. These patterns suggest complex interactions between the star's magnetic field and surrounding plasma that could indicate an impending major outburst. Even more concerning is the discovery of roaming magnetars, neutron stars ejected from their birth locations now traveling through the galaxy at high speeds. In April 2025, Hubble revealed SGR 0501 plus 4516, a magnetar moving through space with no clear origin. Such objects raise the disturbing possibility that a magnetar could approach our solar system unexpectedly. To understand NASA's intensive surveillance of dangerous stars, we must examine how stellar radiation threatens life on Earth. The key vulnerability isn't immediate incineration, but the systematic destruction of our ozone layer, a process with devastating consequences for all life. Earth's ozone layer, concentrated in the stratosphere between 15–35 kilometers above the surface, is crucial to our planet's life support system. This thin shell of O3 molecules absorbs most of the sun's harmful ultraviolet radiation, particularly the dangerous UVB and UVC wavelengths that damage DNA. The ozone layer depends on a delicate chemical balance. Oxygen molecules in the upper atmosphere are split by UV light into individual atoms which combine with other O2 molecules to form ozone. This ozone is continuously created and destroyed in a natural cycle, maintaining stable concentration. This balance is vulnerable to high-energy radiation from stellar sources. When gamma rays and X-rays from a supernova or magnetar penetrate our atmosphere, they break apart nitrogen and oxygen molecules, creating reactive nitrogen oxides that catalyze ozone destruction. The chemistry is terrifyingly efficient. Nitrogen dioxide and nitric oxide act as catalysts, destroying thousands of ozone molecules each before neutralization. The process is self-sustaining. As ozone thins, more UV radiation penetrates to lower altitudes, creating additional nitrogen oxides and accelerating destruction. Computer models suggest a nearby stellar radiation event could deplete 25 to 75% of Earth's ozone within months. The effects would be most severe at the poles, but would affect the entire planet. The biological consequences would be catastrophic. With compromised ozone, Earth's surface would face unprecedented UV radiation levels. Phytoplankton, which produce half our oxygen and form the base of oceanic food webs, would be devastated. Their collapse would trigger cascading extinctions throughout marine ecosystems. On land, crop plants would suffer severe damage. Corn, wheat, rice and other staples would experience reduced yields and increased disease susceptibility. The global food supply would face unprecedented disruption simultaneously, with marine food source collapse. Human health effects would be immediate. Skin cancer rates would skyrocket. Eye diseases would become epidemic and immune systems would be suppressed, increasing vulnerability to infectious diseases. Recovery would take generations. Even if the radiation source ceased, the damaged ozone layer would require decades to recover. During this period, life would need to adapt to a fundamentally altered environment, with many species facing extinction. This scenario is scientifically plausible. The geological record contains evidence of mass extinction events potentially triggered by nearby stellar explosions, including the late Ordovician extinction 450 million years ago that eliminated 85% of marine species. As we conclude our journey through the universe's most dangerous stellar neighborhoods, one thing is clear. We live in a cosmos both magnificent and terrifying, where the same nuclear processes creating life's elements can unleash forces capable of sterilizing entire worlds. Betelgeuse, the red supergiant capturing our imagination and NASA's attention, perfectly represents humanity's relationship with cosmic threats. It's a star whose eventual explosion will be visible in daylight, yet distant enough to pose no direct threat. It reminds us of our cosmic place while reassuring us we're currently safe. But Betelgeuse is just the beginning. The potential Beetle Buddy companion has opened new chapters in our understanding of stellar evolution and the complex dynamics governing massive stars' final moments. This search has pushed astronomical observation boundaries and revealed new complexity in objects we thought we understood. Magnetars represent a different threat, more immediate and unpredictable. These cosmic monsters, with their quadrillion Gauss magnetic fields and capacity for violent outbursts, remind us the universe contains forces beyond comprehension. The closest magnetar lies just 8,000 light-years away, exhibiting behavior that could herald a major outburst. Yet perhaps most remarkable is humanity's response to these threats. NASA's Stellar Surveillance Network represents one of our greatest achievements, a coordinated effort to monitor cosmic dangers across the electromagnetic spectrum using our most sophisticated instruments. From Hubble's ultraviolet observations to IXP's polarization measurements, we've built an early warning system spanning the solar system. This surveillance serves multiple purposes. Practically, it provides warning time for cosmic catastrophe. More profoundly, it represents our refusal to accept cosmic threats passively. By studying these dangerous objects, we transform them from sources of existential dread into subjects of scientific inquiry. Knowledge remains our best defense against the unknown. The universe is vast and filled with wonders and terrors. Somewhere, a star is dying in an explosion that will outshine 1 billion suns. Elsewhere, a magnetar builds toward a starquake, releasing more energy than our sun produces in a year. Their light races toward us across the cosmic dark, but we are not helpless observers. We are a species that has learned to split atoms and peer across billions of light years. We have transformed ourselves from cosmic victims into cosmic investigators, gaining something more valuable than safety: understanding. The star that NASA watches 24/7 is not just Betelgeuse, but the universe itself. A vast, dynamic cosmos we're only beginning to comprehend. Every observation brings us closer to answering fundamental questions. What's out there? How does it work? What does it mean for us? In watching the stars, we're not just monitoring threats, we're preparing for our future among them.